Okay, so by the way, Professor Itzik Ben Israel is here, but he decided that he prefers to hear the talks than give the opening remarks. So we are going, I want to now invite Professor Artur Ekert for the second lecture on value inequalities from curiosity to security. Thank you.
Well, thank you very much for inviting and having me here. It's I always enjoy coming to Tel Aviv, not only just to meet friends, but somehow, you know, just the place has a certain vibe to me, whatever that is. The talk that I kind of had in mind for this particular meeting originally sort of was kind of like a popular talk about the device-independent quantum key distribution. So my idea was to show you how the whole thing evolved. And when I started putting together material for this talk, because at some point I decided, okay, well, I gave a number of talks and I had a template prepared. And I was kind of bored with this template myself. I think, well, okay, it's easy, I can give another popular talk. But let me just sort of like revise it. Every now and then you go to your favorite talk and you try to sort of kick new life into this talk. So that was the case. And then I realized that over the last, actually, few years, the experimental part of quantum cryptography, especially device-independent, the most extreme form of secure communication, made enormous progress. And not only that, it was just a progress that borrowed those experimental techniques, borrowed from all kinds of interesting new developments. And I'm not an experimentalist. I used to work with experimental colleagues a lot. But I always find it fascinating that something that you as a theorist think, okay, well, this is a problem, and obviously it's going to take a while to overcome this problem. Nonetheless, our experimental colleagues can sort of like pick up and deal with it in a beautiful way. So what I'm going to show you is a bit of a half-baked, because I didn't actually have a time to complete this talk, so there may be little inconsistencies in my slides, but please bear with me, okay? So essentially, sort of to set up the scene for this presentation is, I have just a pure academic interest in the limits of secure communication, the limits of privacy. And it's interesting that the two topics so I'm going to present you two different narratives that kind of nicely merge and focus on this very problem. One narrative is a curiosity-driven research, which is mostly about understanding quantum physics. And so that will take us into the notion of randomness, understanding randomness in the context of quantum. And the other narrative is about the quest for security, how to design a perfect cipher, something that nobody can decipher. And you may notice, by the way, that in the first narrative, I just put some pictures, and you can probably easily recognize most of those people. And in particular, one of your own, because I put Boris Cyrils on there. I understand he was a professor here at Tel Aviv University. And I think he's somehow underappreciated in the whole story, because his work, his mathematical work on the nature of Bell inequalities is sort of being rediscovered now and put into good use. And I think it will be very difficult to push device-independent quantum crypto. Probably he never thought about device-independent quantum crypto, but certain techniques, certain perspectives that he developed became very important for us to understand how the device-independent quantum cryptography may work. And then, the two narratives will fuse together. So the first one, again, one can give the whole lecture, a series of lectures about the history of cryptography, so I'm not going to do that. It's just like one slide with a big question. Is it possible at all to design a system where you can convey messages with absolute security? And people thought about it, and the whole story of secure communication goes to ancient Greeks. They came up with a device called skittily, where they just simply wrapped a strip of parchment around a wooden button and just carried to another person who had the same kind of, or wooden button of the same diameter. Then the story of substitution ciphers and mechanical devices that people use, culminating with Enigma that you most likely heard about. The thing is, whenever humans manage to come up with a device or a method for pretty good encryption, sooner or later there was another clever individual who came along and said, actually, you know, this can be broken, and came up with the idea how to do that. And the question remains, is it then possible to design a method which is unbreakable? And the answer, surprisingly, is actually yes, with a little bit of a caveat here. So there is a cipher, and again, most of you probably know about this, but let me just mention that there is a system called one-time pad, where you just write a message in a binary, and you meaning like two individuals in this case, like we call them Alice and Bob, who want to communicate with each other. We assume that they manage somehow generate a truly random sequence of zeros and ones. And this binary sequence, they have two identical binary and completely random sequences of zeros and ones. And whenever Alice wants to send a message to Bob, she simply picks up a message, writes it in binary, and then she does binary addition. So she adds bit by bit, each bit from the message plus each bit from the key, and generates a cryptogram. Now, the randomness of the key, the red sort of sequence of zeros and ones that you can see here, is transformed to the randomness of the message. So no statistical analysis in this case will reveal any statistical pattern in the cryptogram as long as the key is truly random. So then Alice sends this cryptogram to Bob, who has identical keys, so he can subtract this randomness from cryptogram and get the message. So this system, as long as the key is truly random, it's identical, and it's only used once for each message. So once you use the key is just thrown away. And you have to be very careful how you throw away keys, by the way. That's the more practical side of the story. And then you have to just start with a fresh key. So it was then shown that under those assumptions, of course, the key has to be secret, known only to Alice and Bob. So Claude Shannon, the founder of information theory, but also cryptography, modern cryptography, showed that this system, known as a one-time path, because you are supposed to use key only once, is absolutely secure. You cannot just break it, as long as you can satisfy those assumptions, which is fine, you know. So we have the answer to the question, where is the problem? The problem is with the key distribution, because each time you have to regenerate those keys, so that has to be done in such a way that the key is delivered to two or more parties somewhere, separated from each other by a great distance, perhaps. And then, so how are you going to do that? So that's the big thing called the key distribution problem. Solve the key distribution problem, you have a perfect cipher. And you know, people in cryptographers tried, and they came up, and here, you know, another lecture about public key crypto system, beautiful mathematics that allows you to bypass this by creating two keys, one public, one private, and so on and so forth. However, and here quantum comes again, with quantum computers on the horizon, many of them, not all, but many of them might be simply not secure. So hence a need to design a system which is not based on something that is known as a computational complexity, but that kind of information security background. So in other words, find a good key distribution problem. So again, there's much more to the key distribution problem. Essentially, the key distribution problem, mathematically speaking, amounts to the following question. So suppose Alice and Bob somehow, by some method, try to generate truly random and identical sequences of numbers into different locations in their respective location. So they may be not perfectly correlated, there may be some errors. The question is, can they estimate how much of this sequence that they share is known to someone else, to another entity, to a big enemy called an eavesdropper, right? So unfortunately, within sort of a classical realm, there's no way, there's no physical signature in the generated binary string that tells you how much information could have leaked to an eavesdropper. Because once you know, once you have these numbers, as I say, the key distribution doesn't have to be perfect. But once you know how much it is, to what extent it's compromised, then computer scientists came with a number of beautiful mathematical techniques that allow you to clean the key, so you can do error correction, and then you can also make it secure by something called privacy amplification. So those things are known, but you have to start, and then you cannot just start using those techniques if you don't know how much information someone else knows. So once you have this, the rest is doable within classical means, but this part is the key thing. So the question we are really asking here is it then at all possible to estimate from degree of correlations between two binary streams or some other statistical test perhaps, how much information about this key is known or can in principle be known to someone else? So let's remember this question, and then that brings us to sort of like the notion of randomness, because we are really truly asking is how much randomness, unpredictability, uncertainty is in that key. And then when it comes to, and here we'll be coming to a very interesting point that we are going to address, so then another lecture about philosophy of physics will just come here. It's about the nature of this randomness. So when you think about randomness, do you think that there's real, genuine randomness in nature? Or is it something only perceived? And this sort of like dichotomy, this way of looking at randomness is actually quite old. It goes, as everything in Europe, right? It goes back to the Greeks. So the Greeks thought about it, and there were two schools of thinking. One is that Epicurus, in fact, thought that randomness is objective. It is out there. He says atoms swerve at random along the path. And that was contrasted with Democritus, who said, well, no. It's atoms, as Greek understood them, actually follow predetermined paths. So randomness, according to him, was simply a perceived thing. So something that simply, it happens, there is a causal relationship, things go in a predictable way. You don't know the whole story, so sometimes perceive the whole thing as coming out of the blue. It doesn't mean that it really came out of the blue. It simply just means that there was a reason, but you don't know, so you perceive it as random. So those two different schools somehow persisted, and of course, most of us, if not well, maybe until quite recently, most people say, well, actually, randomness has to be epistemic. Those things are really predetermined out there because the whole body of knowledge, I mean, the whole purpose of understanding nature is to find causal relationships, right? So we want to really be sure that when we say we understand something or that we have some laws, that means that we can relate one event to the other, or we can always say this event had a history, right? It happened because of something else, and that something else happened because of something else, and then the whole causal chain of things. Now, but it seems that when you apply this kind of naive, at least, way of thinking to quantum phenomena, you are hitting the wall. So, and one person who in particular was not very happy with the whole thing was Albert Einstein, who just paraphrasing his ideas into this simple experiment, the randomness in quantum seemed to be of a slightly different nature. So it was truly by the way quantum mechanics was formulated with the concept of states and measurements and so on and so forth. It was impossible to make precise predictions. So the best you could hope was a statistical prediction. So if you take the very simple example of this particular experiment, where you have a photon that you prepare, this photon is impinging on our beam splitter and can be reflected or transmitted. And in fact, it doesn't split into half. One of the detectors that you place, either in reflected beam or transmitted beam, will fire. So that means photon will end up somewhere. But you, a priori, even though you may assume identical preparation, so think about the Platonic experiment, right? Not the real one. So the preparations are identical. They're described by the same quantum state. Nonetheless, the final outcomes can be different. And that's something inconceivable in classical way of thinking, right? Because we say, okay, identical preparations lead to identical outcomes. But that's not the case in quantum. So then Einstein said, well, you know, that's because the whole story is not complete. The quantum specification of the states is not complete. It's missing something. There may be some other variables, some other parameters that you don't take into account. Had you sort of taken them into account, you would have made predictions that work, so that you would be able to say whether these things bounced or got transmitted. So call them hidden variable if you want, right? Moreover than that, Einstein said, well, those variables are just local, you know, they are there, they are at the photon level. I mean, the photon doesn't react to some parameters that are miles away. So Einstein was not against quantum theory, but he was simply saying that we have to work harder. It's just not the end of the story. And that seems to be like that he voiced this concern in his discussions with Niels Bohr, but also in this famous EPR paper written in 1935, together with his two colleagues, Podolsky and Rosen. Now, you know, that what looked like a purely academic questions became something that, due to John Bell, was turned into a viable experimental proposition, in a sense that you can falsify this statement, right? You can set up an experiment, and that's amazing that you can do it, where you can falsify local hidden variables. And that would happen, and then again, you know, here there is a conventional narrative about how you can derive the Bell inequalities. There are many versions of Bell inequalities and so on and so forth. But let me just sort of put a slightly different modern twist to this, because I want to make the connection to crypto later. And this is how, especially, you know, when computer scientists discovered Bell inequalities, they were not very happy with the original formulations, and in fact, they preferred to connect it to something called games played by a few people. But in fact, physicists also thought about game. One of my colleagues, actually from here, Lev Weidman, told me about his concept of, or his way of understanding Bell inequalities in terms of game, long before I heard this formulated in terms of computer scientists or CHSH games. Anyway, so never mind. So here is a simple diagram. So I want you to think about the Bell inequalities, having in mind the following scenario. There's Alice, there's Bob, two physicists miles away from each other, and they have a device to which they can input a number, say 0 or 1, so it's a binary. So this device takes two inputs and generates two outputs, also 0 and 1. So X is a binary, A is binary, and the same for Bob. Bob has the same device. Y is a binary 0 or 1, and outcome B is a binary 0 or 1. Now, when you have devices like this, and Alice and Bob can randomly prepare inputs X and Y, you can describe such a pair of devices by sort of tabulating probabilities. So given X and Y, what are the probabilities of outcome A and B? And you can put it as a matrix. And in fact, you can then define all kind of linear functional on the space of this probability. So by which I mean you can take different entries in this matrix, multiply them by whatever you want, add them together, so that's a linear functional. So you don't have to sometimes even know the whole probability. In this case, there are 8 independent parameters if you look into all possible constraints. But sometimes what is interesting is to know some linear function of those parameters. And the two figures of merit that physicists and computer scientists like is define a certain criterion, call it a game, and tell when this game is won and when it is not, and check what is the probability of winning the game, or parameterize it in some other way. So if omega is a probability of winning a certain game, you may have some other parameters that you may find interesting because maybe they're easier to measure. So in particular, there's the CHS-8 challenge where you say, have those devices, and now you, Alice and Bob, are challenged to design devices so that the outputs and inputs satisfy a certain condition, and this condition is that the binary A plus B is equal to the product of X times Y. Essentially, that means that the outputs should always be the same, except when X and Y are equal to 1, in which case we want them to be always different. I don't go into technicalities of those equations, just to say that it's very easy when you formulate Bell inequalities in this way. It's very easy to see that this condition cannot be satisfied all the time. It just simply, if you have a deterministic procedure, a Boolean function, A of X, and a Boolean function, B of Y, that those devices implement, there's just no way, there are no Boolean functions so that, you know, A0 is equal to B of 0, A1 is equal to B of 0, and then A0 is equal to B of 1. Then A of 1 and B of 1 have to be the same, but we require that they're always different. So clearly, the best you can do is that if you run such an experiment, that your error rate will be 25%. It's kind of, if you just give it a little bit of a thought, you can see it right away. So that's essentially what is a Bell inequality in some sort of form or the other. Now, very briefly, I'm going to connect this to something that would help you to understand the concept behind the device-independent quantum crypto. So if you have those two boxes that you request that they behave in a certain way, and then you run an experiment and you measure a certain figure of merit, like the probability that they really satisfy this condition, as I said, you can describe this by a matrix which has all the probability distribution. And as I said, this matrix, if you put all the normalization conditions and non-signaling condition and positivity condition, has 8 independent parameters. And if you then take any of those and take a statistical mixture, a convex sum of those two matrices, you also get a valid behavior, a valid matrix that describes a possible behavior of the two boxes. So therefore, all possible behaviors, and by the way, the term behavior was proposed by Boris Cyrilson. So all possible behaviors for the convex set in some A-dimensional space. So bear this in mind, and so enough theory for a moment, but this is kind of important because then you can visualize the Bell inequalities essentially go like this. Bell noticed that behaviors that conform to the local hidden variable form a convex set. They are polytopes. So they had flat surfaces in this A-dimensional space. So therefore, they can be easily defined by supporting hyperplanes. And if you have the CHS-8 inequality, which has a certain figure of merit, a certain linear functional has to be between, say, 2 and -2, that means that all behavior should be sort of sandwiched between the two hyperplanes. Take a few more hyperplanes and you define a polytope. So local hidden variables, polytopes. Quantum behaviors, much more complicated convex set, is actually a monster in A-dimensional space simply because it has all possible features that are tricky, and there are flat spaces, there are curved spaces. Anyway, clearly the set of local hidden variable, the convex set, the polytope, is embedded in this larger set of convex quantum polytopes. So when you do this, when you visualize it this way, so that you can easily use a certain linear functional, say CHSH functional, and define the CHSH inequalities in terms of the linear functionals that sandwich the local hidden variable behaviors. And then you can also look the same functionals and look for the maximum values of the linear functional on the quantum set of behaviors. So this is known as a Zerelson bound. And of course, you know, the whole thing is that there is a proper embedding that this local hidden variable thing, this polytope, is really a proper subset of the larger quantum thing. So if you can find a point outside this polytope, so in other words, if you can find a violation of the Bell inequality, of CHSH inequality, if you can find a point which is outside or on the other side of the hyperplane, then you disprove the existence of local hidden variables. And then that, of course, what happened. And there are many experiments, and one can, for me, probably the most important one was the one that Alain Aspect set up. As you know, that people who worked in this field got the Nobel Prize in 2022. It was John Clauser, Alain Aspect, Anton Zeilinger, but many others were probably also should be considered for this, to mention only Nicolas Gisin, Jian Wei Pan, Roel Hansen, and two colleagues of mine from the Defense Research Agency in the UK, John Rarity and Paul Tapster, who did some of those experiments, not always in public domain, but those are beautiful experiments anyway. So now to bring those two narratives together, the violation of the Bell inequality actually show us that, in fact, there is probably, however you think about it, that you know, sort of is pushing us in the direction of looking at the randomness as something objective. It's not only about, you know, this random variable or local hidden variable it's not that it's not known to someone. It's not known to any entity whatsoever. So there's no entity in the known universe that has this knowledge, right? And the beautiful thing is that you can now re-engineer and estimate the amount of information that could have leaked to outside, regardless who that is. In the worst case scenario, you assume it's an eavesdropper Eve, and that can be done just by looking at the degree of the violation of the Bell inequality. So I'm not going to show you the derivation, but that requires a little bit of mathematical gymnastics, but it can be done. You can just simply estimate how much information could have leaked, and therefore you can actually use all those techniques to distill a secret key from that. So that's is sort of the original, or sort of my approach to quantum crypto. It's fair to say that some other approaches based on the Heisenberg-Anseti principle or no cloning were proposed earlier by Charlie Bennett and Gilles Brassard, and even and they sort of were inspired by work by Steven Wiesner. But the reason I took sort of my approach, not only because it is my approach, but because it leads further. So I didn't quite anticipate, I have to say, when I started working on this, that it is such a strong statement that this derivation of the Bell inequalities from the loss of, or the leak of information from the violation of the Bell inequalities is such a strong statement. It just shows that sometimes, your ideas are more clever than you are, in a way that you cannot anticipate certain things, and your colleagues actually pointed out to you. Anyway, so we started, in collaboration with what used to be called Defense Research Agency in Malvern, which is not that far away from Oxford. We set it up and demonstrated that indeed one can use Bell inequalities as a test for eavesdropping, or the degree of eavesdropping. Sometime later, it took a while, almost I would say 10 years, but a colleague of ours, Nicolas Gisin, managed to not only improve all those techniques, but he was probably the first one to put it on commercial footing. So those who do QKD today probably owe a lot to Nicolas Gisin. And finally, much to my amazement, not so just a few years ago, the Chinese colleagues managed to put the whole thing on the satellite and distribute the key over thousands of kilometers to 2 different ground stations using entangled photons. And so how much more time do I have? Sorry. 5 more minutes, right? Thanks. So the whole thing is certainly secure, but there are, of course, assumptions. So when I was working on this, I knew that the source of entangled photons or entangled particles doesn't have to be protected. But I simply assumed that the devices that Alice and Bob have are carefully designed and Alice and Bob know what they are doing. So certainly in sort of my original version, Alice and Bob control and trust devices in the labs, and Alice and Bob also can make random choices, and the labs are secure and there are no information leaks in this point. However, it turns out that the second assumption is not necessary in this context, and I didn't see it coming. So Alice and Bob do not have to control and don't even have to trust devices in the labs, because the violation of the Bell inequalities is enough to reassure them that the devices are working as required. And this insight, indirectly, we owe to Boris Cyrilson. So the thing is that if you have a convex set, just to give you intuition, why is this the case? If you take a convex set and you use linear functions on this convex set, and at some point you see maximum, so say you see that Cyrilson bound, the maximum violation of the Bell inequalities. Then, as you can see, I visualize here linear functionals as a set of hyperplane of the same value of the functional. So think about like the whole family of hyperplanes cutting and slicing this convex set. So when you go to the maximum, and this maximum is such that it's a single point. It can be, of course, the hyperplane as well as the minimum is, but if it is unique, which we call exposed point, then it is unique, right? So at this point, you are tangent to just one behavior. So the maximum of the functional or minimum of the functional identifies one single point, or many of them sometimes on the flat surface, but that we can exclude. If we can see by the construction that we are not in this flat regime, but in the other one, that just picks up just one, not many, one behavior, up to some local isometries. And that's the whole idea. So once we can actually reach a certain type of the violation of the Bell inequalities, we know that there's only one way of doing this. There's this one particular behavior that is responsible for generating the whole thing. And using this concept, which is sort of like generalizing something that is called the Cyrilson bound, we can actually remove the second assumption and design that truly device-independent quantum key distribution where we don't even have to trust our devices. And to prove the security required a little bit more mathematical gymnastics, and I think the significance of the final proof, I would say, was proposed by Rotem Arnon Friedman, currently, I think, somewhere in a superposition between the Weizmann Institute and Geneva, Renato Renne and Thomas Vidic. Now, to take this to practical implementation, so that's yet another lecture, in fact. It's something that, but let me just show you the latest, because I was very much impressed by the most recent result, which just appeared. And this is work of kind of international collaboration, but mostly driven by people from Hefei, from China, where they show device-independent quantum key distribution over 100 kilometers with using techniques which are very interesting. And one is almost tempted to look at this particular experiment and look at different components of this experiment. And you can tell a story of each of them. So for example, there's magneto-optic trap, they use optical tweezers because they entangle rubidium atoms, not photons. Simply because the detection is much better. So then you have two traps in two different locations, and then in each of them you have rubidium atoms. You use collision blockade loading, which is another beautiful technique which allows you to essentially remove all pairs of atoms, because when you load the trap, and you only end up with either one atom in the trap or no atoms in the trap. So that's a beautiful techniques of loading. It's just due to light assistant collision, simply atoms which come in pair to this trap, being exposed to a certain frequency, just get too excited, want to form the molecule, and acquire some kinetic energy and just leave the trap. Then the beautiful another component one can tell a story about, which is related to down conversion here. So the idea is to take the frequency from the typical rubidium fluorescent light that they get and gate it to the telecom 1.3 micron regime, where you have in optical fibers lower losses. And then the heralded entanglement, where you use a single photon coincidence, single photon interferometry there to infer about the existence of entanglement and so on. I usually, as a theorist, when I come and work with experimentalists, I want to get some kind of ideas about the orders of magnitude. So I usually write this kind of diagrams for myself, where I have a schematic. This is my way of understanding this experiment and the time scales involved. So I just don't have time to go through this. But then, to say that today we are getting to the point where it is indeed possible to have a positive secret key rate over distances of hundreds of kilometers. And having a device-independent key distribution is a beautiful technique, because in principle, you don't have to trust the provider of the devices. In practice, of course, you would shiver a little bit and probably wouldn't buy those devices from people you don't trust. But in principle, you can purchase devices, run the statistical test, and the devices sort of certify themselves. Is it the end of the story? Well, I think there will be, in years to come, a wonderful progress on the technology side. But I think there's still lots of interesting basic work to be done there. One would be just look at the superdeterminists, maybe, and thinking how it may, what is sort of, well, I'm very skeptical about this attitude, but certainly much more interesting would be just to redefine security randomness in the context of secrecy and multiverse using the Everett approach. I don't think I'll just want to go any further. I just wanted to say that device-independent quantum key distribution is pushing secrecy to the limits. I don't think there are any better systems, at least on the academic side. How practical they are, how useful they are, all time will show. I think that what is interesting that the quantum technology over the last decade or so allows us to implement this at the level which is almost commercially viable. Whether there will be market for this, whether this will be useful, who knows. But from the academic perspective, certainly watch this space, device-independent quantum key distribution. Thank you.